an electromagnetic field, how to use work planes, how to import material properties as functions, and how to use perfectly matching layers for scattering boundary conditions. So first we open Comsol. It's going to be a 3D geometry. We click next on the model wizard. We're going to work with radio frequency electromagnetic waves. Click next and it adds it automatically. And we're going to work on frequency domain because we want to see how it scatters certain wavelengths. Our geometry is going to be in the nanometer region. So we're going to build a sphere of 15 nanometer radius. Build selected. It automatically knows that it's 15 nanometers. It just says 15, but because in geometry we define that we're working in nanometers. If you want to see your geometry bigger, you click this button here. It extends the zoom to your entire geometry. So now let's say that we want to put the sphere on top near a glass slide. So we right click in geometry and select work plane. Now it gives us here which work plane we want. Right now it's by default selecting XY. But in this button, when we click it, we automatically go to a YZ view. And it's very convenient, so I like the YZ plane. And it's going to be in X equals 0. So we want to see how things look in this geometry. And then we don't see our nanosphere, but we can always zoom extend and it'll appear. So I'm going to zoom out a little bit. And now I want to build my glass slide like so. And I'm going to go to geometry and I'm going to revolve this glass slide. So it likes to revolve around this axis. So that's why I don't build the whole glass slide all the way here. It's okay to build it just to here. So right click in geometry again, revolve, and it's telling us that it's going to revolve whatever we drew in the work plane WP1. So we drew the glass slide. It's going to revolve 360. So build it, and there's our glass slide. We zoom out. Perfect. Now because we want to study the scattering not only inside these domains but all around them, this needs to be a domain as well. So we need to enclose our two geometries so far in another domain. Because this is a sphere, I expect that the scattering is going to have spherical symmetry. So I'm going to build a new sphere. This sphere, I'm going to make it a little bigger, maybe 120 nanometers. And I'm going to put a layer of 30 nanometer thickness and build all. Now I zoom out. If I want to see what's inside, you can select here different types of selections. So right now it's selecting objects, so it selected the whole sphere. If we click this one, it will select domains, and it divides the domains automatically. Clicking this eye with the backslash hides the selected geometry, so we can see inside what we built. And that the layer automatically built a second sphere, so we don't have to do it on our own. And once we have domains inside domains, Comsol automatically knows that they are separate, so we don't have to subtract or anything. I'm going to turn the lights off. I don't like the lights. This other button makes it transparent, so it's also helpful if you want to look through. And this one is just the wires, is wireframe. So we're done with the geometry. Next we have to define materials. So open the material browser, built-in material, air, right click, add it. and then it automatically tells you all domains. That's okay. Everything is air so far. But then we're going to add a new material. This material is going to be glass. We want to select the glass slide. Left click selects it, so we can either add it like this, clear selection, or we can left click to select and then right click and it adds it automatically. So because we said we're working on E&M waves, Comsol automatically knows that it will need the electroconductivity, relative permittivity, and permeability to calculate. So I'm going to enter the values. Epsilon, let's say it's 2 for this glass, and no magnetic properties, no conductivity. That's very close to glass. And then, well, we can change the name of the material, rename, and call it glass slide. And then a third material, it's going to be silver. So we got it. Now for the properties of this material, we can do it wavelength dependent. So for that, we have to come to global definitions. We realize that we want maybe to shine different wavelengths of lasers, different frequencies. So then you want these properties to depend on the wavelength. Sigma for now is going to be 0, mu is going to be 1. So mu equal 1 means that we're not interested in magnetic effects. They're negligible. The biggest effects are going to come from the relative permittivity. And the relative permittivity, if we look at the equation, so if we write an imaginary part, it's this same thing. It's conductivity divided by the frequency. So once we input the imaginary part of the epsilon sub r, then we don't need to put the conductivity, otherwise we will be inputting things twice. So that's why sigma is 0, because it's going to be here. In epsilon r, we're going to put an imaginary part right away. So then we have to define that. Right click on global definitions. E0 is going to be the magnitude of the electric field. Voltmeters are the units of the electric field. Lambda is going to be the wavelength. Let's say we're going to shine 532 nanometers. I'm going to leave it for now without a unit. And then we're going to input, so right click, functions, interpolation from file. So right here I have a data from Johnson and Christie with the dielectric constant of silver, and then we're done. And then we wanna bring in the real part. Smooth this because I smoothed it out. We're done. So if you want to see how it looks like, you can plot it.